Okay, welcome. This is Dr. Morton, and I'm recording the video for Monday, October 10th, 22. So let's see. Let's first go ahead and take a look at the syllabus. So there it is right there. And what you'll see is we're in week 8 of the semester, which is amazing. There's not too many weeks left. We only have to go through 8, 9, 10, 11, 12, 13, and then 14 is 14. And then 15 is final week. So what is that? 11 or 10, 11, 8, 9, 10, 11, 12, 13, 14. So 7 more weeks. That's it. So we're more than halfway, or we're, I guess, exactly halfway, not counting finals. Okay. Okay, so what we're going to do is we're going to talk about pick up where we left off on Friday in the video, which I did Sunday, which hopefully you've watched, and we're going to talk about how we do flip-flops. Well, we're going to pick up where we left off. So we're talking about flip-flops. Remember, flip-flops are the critical component of all of our sequential designs, because that's where we store the state in some form of encoding. That's how we store the state that we're in. So when we get to the last third of the course, after we finish our group project presentations next week, and we finish and then we take our test the following week, then we're gonna charge into the last third of the course, which is sequential design or state machines. And flip-flops are integral to state machines. That's how we know what state we're in. We basically encode it in our flip-flops in some way. Okay, and we'll talk about that more then. So let's pick up where we were. So we were talking about actually not this one, but this one. We were talking about our master-slave JK flip-flop, and so there's a lot of things to think about with respect to this one. First off, and I went over this on Friday in the video, and so we'll just cover it fairly briefly again. Okay, so we covered most of this, but so I want to show you a couple things. So let me transition over here. So this is the standard JK master slave edge triggered flip flop, and again we went over this on Friday in the video, but the edge triggering comes because of this inverter here. When the clock is high, then the clock's inputs to these AND gates allows for at least one of them to be able to be turned on. So you have the output here from Q gets flipped back to the K input, and the output from Q bar gets flipped back to the J input, which means that R and S can never be one at the same time, basically, is the bottom line. And then so only one of these AND gates can never be active at the same time, because Q and Q prime will always be the opposite. And then if the clock is high, and say this input's high, then if J is high, the S will be high and the R will be low, and you'll set the flip-flop. And vice versa, if this feedback, if Q is 1, then this input from the output will be high. Say K is high and the clock is high, then this R will be high and the S will not be, and so you'll reset the flip-flop, you'll clear the flip-flop. So and then when the clock goes from high to low, the inverter causes these two inputs from the clock to be 1s when they were 0s, and that allows the Q bar and the Q to propagate to the R and the S, and let this latch match this latch is essentially what happens. And then of course any change in this is going to be reflected in the feedback, and while the clock is low, then you can set up your new J and K, but they don't get propagated to the R and the S, or only one of them will be propagated when the clock goes back high. All right. Okay, so I want to show you one other thing. Let me transition to the paper. So we write a JK flip-flop sort of like this. Okay, we'll draw a little box. and we have the J and K inputs, and then we have a clock down here, and we've got a clock line, and our output Q and Q prime and Q, or Q and Q prime, whatever. Now, if we take these two inputs and we tie them together, then that makes a T flip-flop. If, on the other hand, we want a D flip-flop, we have to put an inverter in, not the J line, we have to put an inverter in the K line. So if D is 1, J will be 1 and K will be 0. If D is 0, J will be 0 and K will be 1. And so if we write the little truth table for this, and my pen's running out of ink, I think mostly because I didn't get it up. And I don't think this one's working at all. No. So we'll just do it like this. So if we write a little table, okay, so this is Q, and this is J, and this is K. So if they're both 0, Q holds. It stays the same. If J is 0 and K is 1, then it's going to clear. And if J is 1 and K is 0, it's going to set. And if they're both 1, it's going to toggle. Now this is what I want you to remember about a JK flip-flop. And the interesting thing is, this part in here is basically the D part, and this part, these two parts out here are basically the T part. Because the T input, if the T input equals 0, then the flip-flop holds. If the T input equals 1, then the flip-flop will toggle on the next clock input. On the other hand, on the D input, if D is 0, it's going to clear. If it's 1, it's going to set. And so you can think of the JK as being made up of both a T and a D, essentially, sort of. Okay, well, anyway. So that's kind of what I wanted to say. All right, now let's, so we're going to move along here. Okay, so that pretty much what I wanted to say there. All right, so now we have some characteristic equations, and I'm not going to ask you to memorize these, but I do want you to remember this table for the JK, that 0, 0 holds, 0, 1 for JK clears, 1, 0 sets, and 1, 1 toggles on the next clock pulse. Okay. All right. Now, the other flip-flops, these are the characteristic equations. The D is really simple, and that's what we're mostly going to design with. Q plus equals D. So whatever D is, that's going to be the next state. Here, if S is 1, then the Q prime is, and then the next Q is going to be set. And if the R is 0 and Q is a 1, then it's also going to be set. It's going to stay set. So this makes it set, this makes it stay set. And then anything else, it'll be clear. And then here's the JK. So JQ prime plus K prime Q. And you can kind of see that in the feedback, okay? If we go back here, these feedbacks are the opposite. So this is really Q prime and this is Q. And so it's really K and Q and J and Q prime when the clock allows for it. And when the clock is low, it blocks this entirely. Which means after the falling edge of the clock here, then it propagates this to this, but it keeps this latch from changing until the clock goes back clock goes back high. While the clock is high, you can change this, but you don't change this because these AND gates are then shut off. All right. Okay, so I think that's good. Now, those are the characteristic equations, and there's a couple of weird things, like you can implement a JK with a D. Well, normally we probably make a D out of a JK. But anyway, if you wanted to turn it back, you can do these AND gates at OR gate, and you can invert the K input. So that makes a JK. It's a little goofy. Here, you can implement a D with a JK, and that's what I showed you before. Invert it into the K, the D goes directly into J, inverts into the K, and then you just drive the clock like normal. All right, how do we decide what flip-flops to use when we're building a circuit? Well, so we have this RS clock latch. We don't call it a flip-flop because there's no clock. It has a latch or a gate typically, or maybe not even. We have a JK flip-flop, a D flip-flop, and a T. The T's don't really exist. They're made out of JKs, and we sometimes use these for timers. We sometimes use these for counters, but basically they don't get used too much anymore. Mostly we use D flip-flops, and the reason we use D flip-flops the most is because they only have one input, so it minimizes the wiring. However, if we use JKs, it usually requires the least amount of logic to implement the logic function for the next Q plus. But the two inputs do increase the wiring. So most of the time, for most things we do, we use D flip-flops. For registers, we use D flip-flops. For state machines, we typically use D flip-flops. For all sorts of things, D flip-flops are sort of the go-to. But the RS clock latch is very useful because it's the fastest latch you can have, and so we use it in these narrow width clock systems where it's a very fast clock. But we have to be careful that we never let R and S both be 1 at the same time. All right. So I've talked incessantly about the difference between combinational design and sequential design, and we're with flip-flops. We've talked about our first sequential device. We are after we finish our projects, then and their tests, we're gonna focus on sequential design from there on out to the end of the course. And there's going to be a lot of state machines on the final exam. And that's really what a sequential design most of the time is. It's a state machine. So we do want to make sure we want to really we're going to hit that hard once we get to that, because this is really the meat of the course, to learn everything we've learned so we can design state machines. Okay. So for instance, a full ladder, 1 bit of A, 1 bit of B, 1 bit of carry in, 1 bit of sum, and a carry out. So that's a combinational device. There's no feedback. There's no clock. In a sequential design, there is feedback. Some of these outputs get feedback into the inputs, as well as the inputs into this sequential network. All right. So a couple of things to be said. The inputs and the outputs can overlap. Okay. The outputs depend on the inputs and the entire history of execution, not just the current inputs. The network typically has a limited number of unique states or configurations called states, and this is how we embed the history of execution. The history of execution, we each result is a state. A really great, the quintessential example of a state machine is a traffic light controller. All of you have sat at traffic lights and watched them go through their various states. There's a state where east-west is red and north-south is green. Then there's a brief state where north-south is yellow, a warning that it's going to red, getting people to stop. And then you have a state, but still the east-west is red. Then you have a state where north-south is red and east-west is green. And then typically you have a state where east-west is yellow and north-south is still red. And then finally you switch back to north-south green and east-west goes red. And then you can add additional complexities to it. You can add sensors that detect cars, or you can have fixed time intervals. You can have turn lanes with arrows, and you can have a time period when you detect a car in the left turn lane that you turn on the left turn signal, and then you have to have a yellow error and then a red arrow to tell them to stop turning left, and all those are different states. So all those different configurations are different states. All right. So almost all of our sequential designs will be synchronous systems. which means they'll have one master clock, or sometimes more than one master clock, but the clocks are usually synchronized then in some way. There is such a thing as an asynchronous system where there's no clock and things just kind of happen. Everything's kind of working in as fast as it can. It just sort of happens. But those kinds of systems are extremely difficult to design, to debug, to maintain, and to change. Whereas a synchronous system is a whole lot easier to do all those things. So for that reason, you won't see very many asynchronous systems. All right, let me, let's keep going here. This is the traffic light example. So I'm not going to, I kind of talked through this already. I did also want to mention this other issue, which is that the fact that we have timing constraints for our flip-flops, and for most of our sequential designs, we have timing considerations. Here we have a D flip-flop. Here's our D input. Here's our clock, and here's our Q output. Now notice, this is a rising edge clock, and this vertical blue line shows you the active edge. That's where the clock is considered the transition from high to low. Low to high, so it's a rising edge clock. And here's another clock right here. It's transitioning from low to high. And then we have some things written in here. Normally in a typical timing diagram, you would see the numbers would all be in a table, because they might change based on what voltage you're operating this at. It might change based on how many outputs are connected to the queue and things like that. And also, there are constraints on the clock. There are constraints on how fast Q can change, and also there are definite rules about how long D has to be present before the active clock edge, and how long it has to stay good after the active clock edge. In this case, 20 nanoseconds before is our setup time, and our hold time is 5 nanoseconds. And that's the same if our D is going from low to high, as it is if it's going. If it's a high input versus, say, a low input. All right. So the clock has some constraints too. The minimum width that the clock can be is 25 nanoseconds. If the clock has a narrower width, then you can't guarantee that the flip-flop's going to latch in the D values and change Q. So that is an important consideration. Also, notice the Q. So in this case, the D is high, so the Q is going to go high. And look, there's a 25 nanosecond delay, and that's usually the guaranteed maximum. And then there's another figure here, 13 nanoseconds, which would normally be the typical. Okay, so there's a typical, and then there's the maximum. So every fabricated part could behave a little differently, and they're saying the average for our parts is 13 nanoseconds, but there might be some that take as long as 25. Now notice, from the low to high transition, that's 25 nanoseconds and 13 typical, but here 40 nanoseconds from high to low and 25 typical. So that's quite a difference. It's almost double the typical anyway. And so as a result, notice it doesn't necessarily take, there's not symmetry here between the high to low transition, low to high transition and the high to low transition. And that's typical. That often can happen. Okay, and notice how everything is referenced here from this blue line, which is considered to be the clock edge, where that clock changes. Now, the reason this is not a vertical line, it's kind of a ramp, is because we've stretched this out to dramatize the rise and fall times and the need for data setup and hold and all that. Okay. And we sometimes call these propagation delays. A more accurate term is inertial delay. All right, we have back in the day when we used discrete parts, we had 7474s and 7476s. The 7476 is the level sensitive latch. So it's basically a flip-flop, but when the whole time the clock is high, D can affect the output Q. Whereas in an edge trigger, we take the value from when the clock edge hits, the active edge, say it's a rising edge, when that rising edge, or it's a falling edge, when that falling edge hits. And we do have these constraints on our D. We have some setup time and hold time requirements, but other than that, D only takes effect at that active edge, assuming that the hold time and setup time are met. Whereas in the 7476, the clock is a level clock. So as long as the clock is, and notice here we have a caret showing that it's an edge clock, and here we don't have that. And if they were, we put a bubble. Notice we put a bubble here if it's a falling edge or a negative edge device. All right. In this case, the clock, when it's high with no bubble, it allows any changes in D to be reflected in Q, minus a small propagation delay. Okay, so there is such a thing as a level clock, a level sensitive latch for a flip flop. We don't usually call it a flip flop exactly because there's no edge clock. Okay, so notice on this, in the 7476, these little blips in D, this will cause the 7474 to go high for the whole period. But here it only goes high and then back low because the clock is still high all the way to here. And so the D can change this whole time. Whereas here, only sampled at the edge. And then once it's done, then the clock, then there's no more change occurring until the next rising edge clock, or falling edge, or whichever it is. In this case, it's a rising edge because no bubble. Notice here, this little blip comes after the clock edge, and it's reflected here. It should be slid down here a little bit, but you see it in the 7476 because as long as the clock is high, it passes this D change through to the Q output. But in this one, the 7474, the standard flip flop, you don't see it because it wasn't valid at the edge. All right, so that kind of that pretty much covers what I wanted to cover. Hopefully, everybody's turned in your truth tables, and hopefully, you're working on your thing on your presentations. Remember to look at the example presentation that's on Blackboard. Let me show you that real quick. Hang on here. Okay, so here is the course, and here's the group project folder, and if you go into this, here's the group project video, and I'm just going to start it. I'm not going to play the whole thing. Oh well, you have to get past this stuff. Okay.
Okay, so this is group 18 with Mason, Vanessa, Eric, Kevin, and George. And our problem is 8.B. So what it says is
And I'll show you how they actually do the K-maps, they do shared terms, and then they do the simulation. They use National Instruments. You can do that if you want.
Created from here.
So I'm recommending Logisim. National Instruments has a little more of a learning curve, but if you already know it, you're welcome to use it. And that was it. And then the
to X4 be highlighted.
Yeah.
Other than that, there.
All right. So they did use they have a 7-segment display here instead of the 16 segment. And then let me also show, let's see if I can do this here. Oh, let's see. Okay, so you notice there's also this hex display for Logisim. Okay, so let me just show you how that works. So hang on one second. So I booted up Logisim. Here it is right here. And then I'm going to download this. Okay, there it is. And it's in downloads. So I'm going to go back to my Logisim. Open this up. It's kind of small. Maybe, let me set this up as a window. Hold on. Okay, set up as a window. And then now I'm going to go in here. I'm going to open. Oh, sorry. You can't see it. My bad. Transition. Okay, now you're going to open. And I want to go to this PC, downloads, and then this hex display. let's see. And there it is. And then if I bring in some power, let's see, where's my wiring? Base, probe, power. So if I have power, so if I, yeah, then I can just connect it. So if I do this, turns that on. If I do this, turns on that. If I do this, turns on that. So you can turn on these segments however you want. They're kind of all set up here. And then but obviously you don't want to turn on all the segments, but there's all 16 segments. So you can use this to display your digits, and you can drive each of these lines that you need to. Now, like if you wanted to turn off some of them, so maybe we'll turn off some of these. So I don't know, maybe we'll turn off this one. Actually, that needs to be off, but say we'll turn off this one. So we'll turn off that one, and maybe we'll turn off this one. We'll turn off this one. Oh, well, I screwed this up, but I'm not going to save it, so that's okay. And then maybe we'll turn off this one, and we'll turn off this one, turn off this one, and we'll turn off this one, and that's it. And no, one more, and turn off this one. And now we have an A. All right, so and you can display your characters like this. All right, so obviously I just connected them all to power. I'm not driving them with the gates, and obviously you'd normally drive them individually, not have a bunch of them grouped together. All right, and we'll do that and discard. Okay, I think that shows what I wanted to show, and yeah. So be working on your projects. If you have any questions, get in touch with me. I'll help you. If you don't, that's fine. And then I'm going to send you, I want you all to present next Wednesday in class. And I'd like everybody to be there. If you're not there, then you're not going to get credit for the group project. So everybody needs to be there next Wednesday. I'll send out an email to that effect. All right, that's it. We'll see you later. We'll see you in class on Wednesday at 2. You don't have to present your project this week. We'll talk about the projects on Wednesday, but you do have to come a week from this Wednesday for sure, in order to be there to present your project, so you get credit. So if you don't come, you don't get credit, unless you're in the hospital or some really good excuse. All right, that does it.